Hello, my name is Rico Tyler and I'm with the National STEM Scholars Program. And I'm here to share with you ways to use phenomena-based science, sense-making, claim evidence reasoning in your classroom. Today, we're going to be looking at a specific performance expectation in the next generation science standards. It's a 6th grade standard, PS2-2, that students can plan an investigation to provide evidence that the change in an object's motion depends upon the forces acting on it. This same activity is also going to hit every single one of the 4 middle school engineering standards. How to define criteria and constraints, how to make a systematic evaluation of different solutions, how to analyze data, and how to do iterative testing. So this combines a lot of stuff into a very simple lesson design. What I really like about this activity is it uses extremely basic materials. To do this activity and incorporate it into a lesson, you need paper, you need scissors, you need a ruler, you also need some sort of timer or stopwatch. Any of those things will work, and you can run a really engaging experiment using this idea that I want to show you today. What we're doing is called paper helicopters. The idea is to design a paper helicopter that will fall as slowly as possible. Now, instead of doing this by just giving kids materials and have them do stuff, students are going to actually run a series of experiments to figure out what design parameters will result in the slowest falling paper helicopter. And I want to keep emphasizing that because usually you think of speed as your goal. Here, we're going for the antithesis of speed. We want the slowest falling paper helicopter. And we're going to do this by testing a range of helicopters. So whilst we're doing testing, we need to do the testing while controlling variables. Here's how we do it. We start with the paper that we use. As you, excuse me, a piece of paper like this, if you cut 4 centimeter wide strips, you can get 7 strips of paper out of this. And cut your paper into strips that looks like this. You could have students do that, but I find that with a paper cutter, which everybody has in their school, you can cut this paper in bulk. To cut the paper helicopter, here's how you do it. You start by taking your paper and you cut it down the middle to make a pair of fins or wings. And I have already pre-drawn this so that we can have, for this particular one, 9 centimeter fins. I'm using scissors, but you can actually do this by simply tearing the paper. Sounds crude, but it'll work. Now once you've done that, you cut your fins, you want to go 2 more centimeters and make what I call the body of the helicopter. After you go down the 2 centimeters, then you want to cut in about 1.2 centimeters on each side, and you can probably see I've marked this for myself to make this easy to do. And then the rest of the helicopter will be a tail. So I start with the tail and fold the tail in. Nice, clean, crisp folds will give you better results. This is pretty easy to do. Not a hard skill for most middle school students. Now I take my fins and I fold one back, like so. And then I flip it over and fold the other fin in the other direction. Like that. And just to make sure I don't forget, I usually mark these with how long the fins are. And these are 9 centimeters. So there's my helicopter. Now, one way, you can drop the helicopter exactly like it is right here. Another way to do this is take a paper clip and clip it to the end. You can drop it either way. I find that the paper clip tends to make the helicopter fall, as you might imagine, a little bit faster. If you're dropping this a long distance, and we'll talk about that a little later on in the video, you may want a faster speed. But there's no reason why you have to do it. But of course, all the helicopters you test need to either have this paper clip or not. So here we have a 9 centimeter helicopter. With the same paper, you can cut helicopters with different fin sizes. For example, right here, this is the same design, Notice 2 centimeter body, but the fins are only 4 centimeters long, and the tail makes up the difference. But both of these are exactly the same size. So they have the same mass. The only variable here is the length of the fins. Here's a helicopter with, I believe I cut these to be like 11 centimeters long. So we can make, usually you'll want students to make between 6 to 10 helicopters of differing sizes. What we want to find out is, how does the changing the length of these fins influence the fall time? Will it make the fall time greater? Will it make the fall time less? That's our goal to do. So once we get this done, then what we need to do is to find a place to drop the helicopters from. We're looking for a location that we can drop them all from the same height, and then measure the fall time. We'll do multiple trials with each length, find an average for those results, and then graph the results and see if there's a pattern that we can discover in the fall time of our helicopter. When you have your helicopters ready, of course you need some place to drop them. The key here is you want some place indoors so that the winds won't be a factor in your fall times. But you also want a place where the helicopters can be dropped a consistent distance. And the higher that distance is, the longer the fall times, and the easier it is to get good data, good measurements. Now you can do this completely within the context of your classroom. You can, for example, put markings on a wall, and students can drop the helicopters from about 5, maybe 6 feet, and that will give you good data. Even better is to go into a gym and drop from the bleachers, because you can drop from the side of the bleachers and maybe have a 10 or 15 foot drop. And that gives you good data as well. Sometimes you have a stairwell. Here we have an even better spot. This is the 3rd floor atrium of Gary Ransdell Hall here at Western Kentucky University. So I've got 3 floors that I can drop from. And so this makes a great dropping location. It's indoors, lots of space. I can have students lined up all over the place here to drop. Now what you're going to want to do is, when they do this experiment, students are going to want to drop each helicopter at least 3 times and get an average for their data, so that you can get a good fall time for each of the helicopter lengths that they're using. Right here I have one that's 9 centimeters long. I've chosen to use a paper clip on this one. You can drop the helicopters with or without a paper clip. With the paper clip, you get a little bit faster speed and a little bit shorter fall time, which is probably not what you want to do if you're dropping from a shorter height. But from a really high altitude like I've got here, I probably want to cut that time down just a little bit. And so that's what I'm going to do here. So to get ready to drop, I'm going to be the dropper, and there'd presumably be another student that's got a stopwatch. Now the stopwatch person can be up here, but oftentimes if you're dropping at this great a distance, it might be better if the person operating the stopwatch is down there somewhere. But to be consistent in your dropping, I usually have students hold their helicopter in a Y shape. That way every helicopter's fins are at the same angle. You're trying to get that consistency in controlling the variables. So we just hold it over here. And then of course if I've got someone downstairs, I need to alert them. Ready, set, drop. Once you've had your data, what you want the students to do is to graph the results, putting the length of the helicopter on the horizontal axis and the fall time on the vertical axis. I have right here an example of just such a graph using actual data. And you can see there's a very clear pattern. And part of it's predictable and part of it is not what you might expect. As the helicopter fins get longer, the fall time gets longer. The helicopter's falling slower. What's happening is when you let go of the helicopter, it falls, and as it falls, it picks up speed until the drag and the lift from the fins equals the weight of the helicopter. At that point, the helicopter falls at a constant speed. That happens pretty quick. And so the helicopter with shorter fins has got to fall faster before there's enough drag and lift to equal the weight of the helicopter. So longer fins slows the helicopter down, gives you a longer fall time. The problem, though, is that only works up to a certain point. And in the graph, you can see, for this graph, somewhere between 8 and 9 centimeters, things start to go wrong because the helicopter structure is paper. Now, a real helicopter has the same problem, even though it's made of a different material. As the blades get longer and thinner, they're no longer able to hold their shape. You'll see this when you drop the longer helicopters. The fins no longer hold steady, they start to warp around, and they're no longer as effective as they were, and now the helicopter starts falling faster again, meaning the fall times get lower. So a helicopter with really long wings doesn't fall very slowly, and a helicopter with really short wings doesn't fall very slowly. There is a peak in here, and through the data, students can discover where it is. Now, if I'm doing this as a lesson, I can then branch off of that and have students use their data to decide what sized wings will produce the slowest falling helicopter, and actually do that as a bit of a classroom competition, trying to do literally a slow fall. Last helicopter down is the one that wins in this competition. And you can actually branch off of here. We've tested one parameter, the length of the fins. We can also test something else. What I've done here is cut some paper to a different size. These are wider strips. We could build a set of helicopters that all have the exact same wing length, but they have different widths. And you'll get, I won't share with you what that one looks like, but you'll see a different pattern here. So you can manipulate the length of the fins, then you can manipulate the width of the fins, trying to find the ideal length and the ideal width. You can go even further. If you want to really milk this activity for all its engineering potential, you can then test different kinds of paper. We mentioned that if the fins are really long, they no longer are structurally very sound. So what if you change the paper? Change from very thin paper to something that's more medium weight to cardstock. And you'll find out that certain types of paper will perform better than others. So you've got a range of parameters that students can experiment with, getting quantitative data, not a guesswork here, and then figure out the ideal paper helicopter, the one that has the ideal wing length, the ideal width, the ideal material. You could even test different weights. This helicopter has a paperclip on it. Turns out that the weight of the helicopter actually has an effect on the fall time, and not always what you think it is. And then, of course, in the end, you summarize that data by actually producing a helicopter with the slowest possible fall time. All of this comes out of a couple of sheets of paper. So it's very effective in terms of the cost to you as a teacher. Students find this extraordinarily engaging. They get to do quantitative research with it. Along with this, if you check out our supporting materials, we have some other materials that goes along with this lab to help you produce it as yourself. As always, thank you for watching.